Hello, my name is Mark Shah. I'm a Principal Hardware Engineering Manager at Microsoft Corporation. Today, along with my colleague Prakash Chauhan, Server Architect at Google, we will introduce you to DC-SCM, which is short for Data Center Ready Security and Control Module. A brief explanation of our goals for this presentation. In the first part of the presentation, I will walk through an overview of DC-SCM, along with how it evolved and its current status. In the second half, Prakash will walk you through why DC-SCM exists, describing its benefits along with its challenges. Let's start with a brief description of common server architecture. The block diagram shown is a typical two-socket server. The number of sockets isn't really necessarily relevant. This could be one socket, a two-socket, or a four-socket. I chose two sockets because one socket is not really much of a challenge, and four sockets is much harder to draw and fit on a single slide. Note that this also could be other managed architectures. It's not limited to necessarily to processors. The diagram shows basic building blocks of a two-socket server. There are two CPUs. The CPUs have memory controllers supporting some number of RDIMMs. The CPUs support some sort of storage media such as SSDs or hard drives. And they support an I/O subsystem with a NIC or other PCIe cards. All of this is located on the left side of the slide. Now to the right, we have a typical management subsystem. This consists of a baseboard management controller, also known as a BMC. The BMC is responsible for a number of base functions, such as fan control, monitoring of system telemetry, and monitoring of power reset and boot status. Now, the BMC is also an endpoint for LPC or I2C, enabling direct host to BMC communication. The BIOS and BMC boot directly from their respective flash devices. Now, this also is shown as a power and reset control FPGA. On some architectures, this is a CPLD, but it's responsible for controlling the power and reset of the entire server and reporting that status to the BMC. I say that this is typical. I'm leaving out a number of smaller details, and there are a lot of smart engineers that have morphed and optimized this architecture for their own systems. Based on this architecture, companies have recognized potential value in modularizing components of the management subsystem so that they can standardize and better leverage their architectures from generation to generation. Or they may choose to consolidate architectures and homogenize their server management across them. I've worked at two companies that have done this to varying degrees. The concepts you see here are not necessarily new, they're just appropriate for where we're at with cloud development. Now, the latest attempt at optimizing this is called Run BMC. This takes the BMC and support circuitry off of the motherboard and puts it onto a modular card with a defined interface to the rest of the system. This provides two benefits in my opinion. It provides adopters with a level of homogeneity for managing servers in their data centers. And it provides companies with a development vehicle for technologies of interest such as OpenBMC, next generation BMC processors, or alternative BMC processors. This is useful for enabling advanced development out of the critical path of programs. This has proven very useful, but a number of advancements in security requirements and innovations in security platforms has spilled over the lines drawn by the previous generations of modular management. Platforms require a trusted platform module for cryptographic key generation. While this isn't necessarily a new requirement, it's often designed in as a slightly more expensive module form factor to enable a platform to support different TPM requirements for different parts of the world. Platforms now require a root of trust processor to authenticate or attest the BIOS and BMC flash. The root of trust industry itself is still in a disruption phase with regards to BMC. Providers are supported by custom solutions while industry works to integrate the root of trust in BMC. No two customers are necessarily doing the same thing. And beyond the strategic solutions such as root of trust, we also deal with a number of tactical hardware fixes as hardware exploits are uncovered. These types of fixes typically aren't able to be absorbed by existing generations and have to wait an entire generation before they're able to be resolved. And then beyond the hardware and software, we have varying physical security requirements for front panel access interface features. Some servers are not allowed to support, say, things like VGA or USB. And even within an individual company's data centers, those requirements can vary from data center to data center. So To better accommodate these changing requirements, we are looking to redraw the lines of modularity and define an electrical and mechanical interface that enables us to take ownership of the management and securities of our solutions, of our servers. This is really the heart of the value proposition for DC-SCM. Now, with that in mind, we began partnering with key companies within OCP to define a modular form factor with the following tenets. Server management and security should be owned by the solution provider. This eliminates the burden from system providers and enables greater homogeneity of security and management across the provider's data centers. 2. The processing modules should be stateless. In order to own security, the SCM must also own, as much as possible, key firmware bases such as BIOS and BMC. Number 3. Solutions should enable flexible and better TTM for products. By putting what is arguably the most volatile of the system architectures onto a module, we eliminate development from the processor module and leverage a common module, SCM, that enables faster movement through the system integration and deployment phase of programs. Number 4, the solution should provide an open platform for innovation and opportunity. Note that the intent of the specification is not to define the security and management solution, but to define the mechanical and electrical interfaces in such a way that hardware providers can more readily meet the widely varying requirements of the solution providers and enable hardware providers greater agility in incorporating the latest innovations. So, where is the DC-SCM currently at? Well, we have submitted revision 0.6 of specification to OCP and will be kicking it off as a subgroup shortly. The 0.6 specification is reviewed by a number of key partners within OCP, and we are grateful for their participation, but we're ready to review to a wider audience. Mechanically, the specification is focused on a front form factor intended to be coplanar to the motherboard and accessible at the front of the system. However, the specification is not limited to this, and other form factors may be considered. There are some proof of concept developments in progress for support of the next generation servers. Below is one concept demonstrating a SCM located at the front of a 1U server. Notice that the DC-SCM sits approximately in the middle, accessible at the front, next to 4 E1.S drives, which are also next to an OCP NIC. The module itself is 90 millimeters wide by 120 millimeters deep. This completes the overview portion of the presentation. I now turn it over to my colleague Prakash Chauhan, Server Architect at Google, who will discuss SCM benefits and challenges.
Thank you, Mark. Hi, everybody. My name is Prakash Chauhan, and I'll be talking to you about the benefits of DC-SCM and why we think this is so important for our industry.
I would like to start with the problem statement. We have diverse customers that need many different types of machines. For example, someone might want a machine that has high single-threaded performance, while another customer might want a huge memory footprint. So in fact, there is a cross product of architecture, scale-up, and configurations that is blowing up the machine counts that we need to support. You could say, why not buy some of these? And the problem here is security, and to some smaller extent, manageability. The current off-the-shelf platforms do not ship with our preferred security primitives. Also, they have distinct management stacks, which makes integration into our fleet very difficult. So in other words, what we have today just does not meet our needs. So how do we solve this problem? So the one solution that we've come up with is to make the manageability and security piece as a separate element, which then ties up all the different machine configurations we need. So it's kind of like the central point around which everything rotates. And that's the DC-SCM. So what the DC-SCM does for you is that it decouples the security element from the compute element. And the benefit of that is that it enables everybody to bring their own security solution without needing the entire industry to support the same security solution. It also allows you to innovate on a parallel path as far as security is concerned. It allows us to have a uniform security solution across all our machines, which could be different architectures, different generations of architectures, or off-the-shelf products. And it also allows us to have different security solutions for different regions in order to comply with their local requirements. In addition to the benefits of security, there are several other benefits with the DCSCM. For example, in development, it speeds up things by simplifying the motherboard design. For example, you have fewer connections, and there is BMC agnostic connectivity, which makes the motherboard design simpler. It also allows us to reuse the DCSCM design and firmware across different architectures and generations. And this reuse is actually allowing you to assume a known good management and security solution, and thus reducing your validation effort. Also, the standard enforces a certain connectivity on the DCSCI, and that well-defined interface definition prevents errors. It's kind of like having a software API to write to. This slide talks about the simplification with DCSCM of the manufacturing side of things. So if you were to put your security solution on the motherboard, it would have to go through a stringent process to make sure that the supply chain did not get subverted at some point. Whereas with the separation of the compute and the management security node, the security card can go through a much more stringent supply chain, while the stateless compute can be sourced from anywhere. It also helps that you have a cheaper and smaller motherboard. The reason behind that is that you have fewer layers, and a cheaper PCB material can be used for DCSCM. Whereas putting it on the motherboard would have required you to spend money on a very expensive substrate, which is driven by high-speed signals such as PCI Express Gen 5 and future interconnect that runs at much higher speeds. The DCSCM also simplifies operations. For example, if a non-volatile firmware device was on the motherboard, the corruption of the firmware might require scrapping of the entire motherboard to prevent unerased non-volatile devices from being shipped to the manufacturer with sensitive code or data on them. With the modular DCSCM, it is easier to recover from corruption because you could choose to scrap the smaller board or ship it through the trusted supply chain discussed in the previous slide. The other advantages are that a single DCSCM can support multiple machines, which simplifies inventory and repairs processes. Also, the uniformity in error logging and repairs procedure, as well as the uniform error indicators, implies that the data center technicians don't need to be specially trained for different machine types. Now that we talked about the benefits of DCSCM, I'd like to discuss a little bit the key principles that helped guide us the design of this interface. So one of the primary considerations was to reduce pin count. As you all know, the BMC connects to a lot of things in the system to gain telemetry and to have access to sensors. And we did not want this interface to blow up. So we said that for standard bus types that cannot be encapsulated, we would carry them directly on the pins. This shows some examples like I2C, SPI, PCI Express, JTAG, USB, etc. The second tenet was to move the most common GPIOs, which are low-speed signals to the BMC, to a serialized interface. And this basically helps us reduce architecture-specific dedicated signals and also helps save on pin count. The most important tenet, of course, is the security and the integration of a root of trust. The DCSCM must have a root of trust and all pathways that can allow it to check out components that are programmable on the motherboard. And finally, the cost is a major consideration because now you're making a modular solution, and typically modularity goes with expensiveness. So we decided to have a very high volume connector, which is robust, but yet doesn't cost a whole lot. The cost factor is also helped by the fact that we go for a cheaper PCB material with a smaller layer count for the DCSCM. Some other principles that guided the DCSCM are flexibility and extensibility. We solve this by providing for a CPLD or programmable device on both sides of the interface, on the DCSCM as well as the processor module. And the purpose of that is that we are not stuck when we have to add more signals between BMC and the motherboard, because we can always have a larger frame of serial GPIOs that can do the job. We also provided for the BMC to have direct access to registers on the processor module, FPGA or CPLD, so that we could read more detailed telemetry or detailed registers that might not be available over serial GPIO. We integrated front panel controls like management Ethernet, console, and power and reset buttons, as these are the connectivity that we need for management in the data center. We also said that there would be no power dependency for the DCSCM on anything except for one rail, which is the 12-volt standby rail. And the purpose here is that the DCSCM owns its own powertrain, and even if it is a plug-in to the motherboard, it is actually virtually independent. We also considered support for scale-up and disaggregated systems. And the solution for that is by allowing multiple DCSCMs to communicate with each other and act in a primary sense and subordinate sense to compose a larger system. So that summarizes the benefits of DCSCM, but there are several challenges as well. And the challenges stem from the fact that people have implemented a management solution or BMC in many different ways over the years. And what we're trying to do is to have a single solution that meets all of their needs, which means that we have to align various industry partners and accommodate their diverse requirements. The second problem is that the technology for management and control is constantly evolving, and platform architectures are being innovated on by the chipset vendors. And so we have to keep evolving the DCSCM or make it so future-proof that these new technologies can be seamlessly integrated. So finally, I'd like to invite everybody on this call to join the DCSCM subgroup and review the latest DCSCM specification and provide feedback. All the relevant links are provided on this slide. Thank you very much for your attention and hope that you will join us. Thank you.
All right. Thank you very much for attending. The chat's been nice and a little bit active. We can, I think, maybe start by summarizing a couple of the questions that we've gotten. Mark Lerner, and Prakash, just to make sure, can everybody hear me?
Yeah, you're loud and clear.
Okay, great. So Mark Lerner with Oxide Corporation is asking about whether or not DCSCM had proven out anything interactions with the AMD designs. Last year, we partnered with WeWin on a single socket modular AMD board that was our demonstration vehicle for DCSCM. Mark, if you'll email me offline, I can get you in touch with somebody from WeWin. I know that Vincent Lee is may be on the chat, and Vincent is with WeWin. He may reach out to you through the chat directly if he'd care to. And then Sanjay asked asked about the DCSCM spec. At the time of the creation of this, clearly we had anticipated releasing the spec to OCP at 0.6 level. The specification itself is in great shape, and we're ready to release it. However, we've had some slowdowns in getting the subgroup kicked off. That was mostly procedural things about where it should land, and so that got delayed. However, if you would like access to Microsoft Teams site that has this specification, please just email me directly, and we can get you access to it. If there are any other questions, and by the way, Priya is pointing out that there is another Mark Shaw in Microsoft, so please mashaw@microsoft.com. If it goes to mshaw@microsoft.com, it will go to the wrong Mark Shaw. And I'll put my email address in the chat just so everybody is clear on it. Violating all the rules about giving out your email in public. Oh, and by the way, yeah, talking is Mark Shaw. Are there any other questions? Okay, if there's no other questions, Prakash, do you have anything else to add?
No, I think if there are no other questions, let's sign off.
Okay, all right, we're going to sign off. Hey, everybody, thank you very much for attending. We really appreciate your support. And again, if you have any questions, you can email me directly, and we're glad to answer any questions. All right, thank you very much.
Thank you.